Great. Thank you. I should warn everyone that I actually have 50 minutes on this agenda, so the coffee leaves at 2:30, so I would coffee up if I unless Heidi's willing to extend the coffee period. But I'm going till about 2:45, I think. So.
We can wait until after.
Just want to be fair to the audience. So I'm Chuck Regan. I'm a research scientist with the Pollution Control Agency. I've been there since 1990. I've been working with the Hydrological Simulation Program, Fortran, since 2003. Here's a 10-year cycle that all the agencies are working on. Like Steve said, most of our HSPF activities fall within the activities under that purple box, the water resource characterization and problem investigation. So here's an overview of my presentation. I'm going to focus mostly on the 5 items that Heidi asked us to address in our talk, but I will be touching at least briefly on what a watershed model is, what the MPCA business needs are for modeling, what is the Hydrologic Simulation Program, Fortran, the history of HSPF development, HSPF model strengths, history of use of HSPF at the PCA, HSPF data input requirements. We have a guidance document for the development of HSPF applications for the MPCA needs. I'm going to go over a few case studies and end with where we are statewide in terms of having these models constructed. So models can operate at different scales. We have some finer scale, site-specific models. HSPF is actually a watershed model. So what it does is it takes the meteorological inputs, the precipitation that falls on land area, and it delivers that water along with sediment and nutrients to the receiving reach. And a receiving model, bathtub that Steve just talked about is a receiving model. HSPF actually is 2 models in one. It's a watershed model, and it also has a fairly sophisticated receiving water model that handles both stream and lake reach. So in our watershed model, we've got across the top, we have these dynamic meteorological inputs, and those inputs are superimposed on the land area, and the land area has a set of characteristics and size, and when precipitation falls on the land area, it will run off. Does this light up maybe? It will run off from the land area to the receiving channel, and that's our non-point source simulation. Then we add the point sources, we dump them directly into the receiving reach. Now, most watershed models have some channel routing. HSPF has a fairly sophisticated algorithms for in-stream processes. So here's the Pomme de Terre watershed again. We've got a gauge, the USGS has a gauge at Appleton there. So that's the only place where we have any really long-term flow gauges. And we have water quality samples, a fair number of water quality samples collected at 10 sites throughout the watershed. But we have to do TMDLs on places where we don't have a lot of information. And so that's why we want to leverage that information with models, because the PCA or the DNR, we can't afford to monitor for everything, everywhere, all the time. So we can't, it's not affordable, it's not sustainable. So what we want to do is we want to be able to leverage all the information that we have to the greatest degree possible. So watershed models in general, they're not a substitute for monitoring. We're not saying we've got models, we don't need to monitor anymore, just the opposite. They're really just a means to extrapolate the monitoring data in space where we don't have data, and in time on days when we don't have data. It also allows us to change watershed characteristics in the real world. Mark Evenson in the Brainerd office, he's running some scenarios right now where he's changing some forests to agriculture and land use. Obviously, that's not something you can do very easily in the real world, but you can do it again and again in a model. And it also allows us to replay past meteorology over and over. None of us will ever be able to go back to 1988 and look at what would have happened during the low flow conditions of 88 if we had changed some of the wastewater treatment plants. We'll never be able to do that in the real world. In the real world, there are no do-overs, but in a model, you can do that. So these are the primary business needs for the MPCA for having watershed models constructed. The biggest are the conventional parameter total maximum daily load studies, and in conventional parameters, there's a constituent that's considered a pollutant. We need to calculate the mass or load of that pollutant, and then we have to figure out how much we have to reduce that pollutant. Dissolved oxygen TMDLs, we're not worried about reducing the mass of dissolved oxygen. We're actually trying to change conditions in the watershed to make sure that a minimum concentration is always maintained. We're going to use HSPF for nutrient criteria compliance. We have already standards for phosphorus for rivers, and standards for nitrogen won't be far behind. And I'm going to show some examples of how we use HSPF to support point source effluent limits, much like Steve has done with bathtub, and also calculated pollutant trading ratios. And there's some other additional uses for HSPF. We've used it in the Minnesota River Basin to come up with MS4, those municipal allocations for the Security TMDL. We've used it to support some of our Stressor ID work, land use planning support, and then some other general uses that just sort of pop up, things like the nitrogen study, the statewide reduction strategy. Also, Mike Burns at the DNR is using an HSPF model in the St. Louis River to help constrain the movement of magnesium and sulfate in the watershed. Back at the turn of the century, we were focusing on TMDLs. We tended to do things one parameter at a time, one reach at a time. And many of these TMDLs turned into PhD research projects. Some of them actually did. And as Galen Reed, we were actually getting maybe 3 done a year, and we were adding 400 a year, so we were moving backwards in a hurry. And Galen Reed likes to say we were on a 100-year plan, and I know I'm splitting hairs, but actually at the rate we were going, it would have taken 300 years. But he's retiring soon, so I'm not worried about it anymore. But obviously something had to give. And so we realized we can't do these, we can't spend all this money, all this time doing TMDLs. We're falling behind very quickly. So something had to give. We had to come up with a better plan. And the plan was, well, let's knock out all the TMDLs in a Huck 8 watershed. We've got about 80 Huck 8 watersheds in Minnesota. Let's knock them out all at once. But we don't have flow gauges everywhere. And one of the bugaboos with TMDLs is you can list an impairment based on graph samples, but you have to state the equation in loads, in daily loads. And so in order to write the TMDL, we can't just look at the concentrations. We need the loads, so we need simulated flows too. So what is HSPF? It's the Hydrological Simulation Program, Fortran. It's a continuous simulation model, so it's not a steady state model like that, but we're running on an hourly time step. All our applications started in 1995, and we try to get them up to close as the present as possible. It represents different land uses with an equal amount of detail. It includes the hydrologic processes from the watershed area to the receiving reach, both over the surface and in the subsurface environment. It simulates stream and lake hydraulics as well as in-stream water quality processes like nutrient uptake by biology and diurnal dissolved oxygen. It's a core watershed model in the EPA better assessment science, integrating non-point and point or basin modeling platform. It's also a core model in the Corps of Engineers watershed modeling system. It was the framework for the highly contested and controversial Chesapeake Bay watershed model. and it's been used in a lot of large area TMDLs. It includes in-channel sediment scour, transport, and deposition. We're able to actually route 9 different particle sizes. We actually route 3 in our application, sand, silt, and clay. And again, it includes those in-stream biological processes like algal respiration, photosynthesis, growth, depth, and nutrient uptake and nutrient release. So here's how HSPF divides up the real world. We've got some pervious surface that makes up most of the watershed, and we've got 3 pathways from the pervious surface to the receiving reach. We have surface runoff. We've got inner flow, which is shallow, storm-driven subsurface flow, and then we have groundwater or base flow. Then we also have a impervious surface module, and we only have surface, since it's impervious, we don't have any infiltration, so we just have surface wash off. And then we have the reach module that again includes things like nutrients and nutrient uptake by biology, and there's some algal growth and depth and exchanges going on with the sediment in the bottom of the reach. So how did HSPF come to be? Well, back in the 50s, there were some flooding problems in Northern California and the state of Washington, and the United States Geological Survey wanted a tool to predict flood hydrographs at places other than the outlets of the Huck Inc. They had real good gauges at the outlet of all the major watersheds, but they wanted to be able to make flood predictions in the interior of the watershed. And the first thing they tried to do is take that outlet hydrograph and prorate by land area. But that didn't turn out very well, and they realized they needed a model, they needed some sort of tool that would take into account the precipitation patterns, what's going on in the watershed, the cover in the watershed, the soil types in the watershed, and also the configuration of the drainage network. What does the channel look like? What's the channel slope? And so in response to that, Stanford University started working on developing such a tool, and the great-grandfather of HSPF, Norm Crawford, he, in his PhD thesis in 1960, his PhD thesis was basically the Stanford watershed model, and it introduced the civil engineering community to continuous hydrologic modeling. There was a similar model, the Hydrocom Simulation Program, that included non-point loading and in-stream processes, came out in the 70s. And then there was actually another model, another group worked on the Agricultural Runoff Management Model, or ARM model. And EPA basically integrated the Hydrocom Simulation Program, the ARM model, and another model, the non-point source pollutant loading model, and integrated the algorithms in those models into what is now the Hydrologic Simulation Program, Fortran. And the first public release was in 1980. The USGS has provided support for utilities that help build the binary files and edit them. There's what's called the expert system, which helps with hydrology calibration. There's another utility that helps you look at model output and make changes to the model input. And again, I already mentioned it's the core watershed model in the basins package, and recently we don't have to go to the DOS prompt anymore. We actually have a Windows-based version now, so I still like to go back to the DOS prompt once in a while, but you don't have to anymore. For people, because now there's a lot of people who don't know what the DOS prompt is. So I'm dating myself, obviously, but that's okay. So why did the MPCA choose HSPF? Why did we think it would make sense to use the HSPF model? Well, in Minnesota, the MPCA is tasked with carrying out the regulatory activities of EPA, and EPA spends a lot of time and effort developing HSPF. So it makes sense that if we're going to be the purveyors of EPA in Minnesota, we would use, and we have to do TMDLs because EPA says we do. It makes sense that we'll use a tool that EPA strongly supports. There's also strong code control. There's only one sanctioned version of HSPF, and it's a code that is rather elaborate and would take a lot of effort to rewrite. Not that it couldn't be done, but there is one official version, and there's always a lot of QA that goes on prior to a version release. And all of the versions are forward compatible. In other words, if you take a set of inputs and you use version 10 and you use version 11, you'll get the exact same results. And that's, I think, being that it's a regulatory agency, that's important because we wouldn't want to have a set of inputs and use version 10 and get a set of outputs that's different if you use version 11. That wouldn't be very satisfying to someone to say, well, we're using this model to determine your point source effluent limit, but based on what version your limit would come out potentially different. So EPA strongly believes that they don't want the modeling community to do the debugging. They want to do it before they release it. HSPF has the ability to represent channels in strong detail. HSPF is a hydrologic model, so we rely on hydraulic models to develop stage discharge relationships. And in HSPF, you have the ability, you build these tables, and you actually have the ability to put in 100 different stage discharge relationships, and that's what drives the water routing. It also has a fairly sophisticated representation of biochemical processes in the channel, and that's obviously important if you're going to do things like dissolved oxygen, TMDL. We also think it's very important to have that hourly time set to help us do DO TMDLs as well as turbidity TMDLs, since as Dr. Wilson said this morning, it's critical that you can, one of the most critical processes is the division of precipitation into surface flow and subsurface flow. So we want as much resolution as possible on that. HSPF is SEMA approved. You can use HSPF for flood hydrograph determination studies. So there's only a handful of continuous simulation models that are approved for flood hydrograph determination studies there. There's the HEC, the Corps of Engineers Hydrologic Engineering Center Hydrologic Management System is acceptable. The TR models are acceptable. There's a USGS PRMS model that's acceptable. SWIM is acceptable in urban areas, and then HSPF and GESHA are approved for flood hydrograph determination studies. So that's another thing that's important. When we have to deal with daily loads, we have to be able to deal with storm events. HSPF is extremely flexible. You can basically do just about anything you could think of in the model, in the base package. But if there was really something you wanted to do that's not in the base package, you can write your own subroutine. They call it special actions, but really, if there was something in the model that you wanted to add that wasn't in there, you could, as long as you know Fortran, you can add. And that's the people who don't know about DOS prompts might not know Fortran. But as long as you can write in Fortran, you can get the model to do you can add any process you want. Obviously, you need a conceptual model first before you can add it to a computer model. And HSPF is very defensible. It's been used, like I said, in the Chesapeake Bay TMDL. USDA sued EPA, and as part of that lawsuit, they claim that HSPF doesn't do what EPA says it does. And so, after a couple of years with third-party lawyers and university professors, they went through the code, they went through the application, and when the judge ruled in favor of EPA and said HSPF does do what EPA says it does. And again, if you're using a model for regulatory purposes, you like to have a model that's been vetted in the courts. It's prevailed in other court cases too, in Connecticut and Delaware. So the history of HSPF at the MPCA, and like I said, I started in '90, so some of this predates myself, but In 1985, the MPCA had to develop a waste load allocation for the Metro wastewater treatment plant, and that allocation identified a need for a 40% reduction in BOD from upstream sources. So the MPCA lead engineer, in conjunction with other federal experts, determined that HSPF would be used to evaluate the reduction scenarios. In 1988, an LCMR, that was before the Citizens. Now, it only had one fee back then. LCMR grant provided the initial funding, and in 1996, the Minnesota River Basin HSPF models were used to support the dissolved oxygen TMDLs, and then in 2003, Larry Gunderson used the HSPF models to support the Minnesota River Basin turbidity TMDL. In 2006, plans were made to apply HSPF outside of the Minnesota River Basin. And in 2008, the passing of the Clean Water Legacy Amendment made funds available to develop HSPF applications statewide. So in terms of HSPF data requirements, I think you can shoehorn most of the data requirements into four loose categories. There's the forcing functions, which is the time series data, time series data requirements. We actually need HSPF, since we're running at an hourly time step, for all those forcing functions, we need a value for every hour. There's also the watershed area characteristics, much of which can be gleaned from GIS layers. There's the information that we use to help determine the configuration of the drainage network, and those three things are all model inputs. We also need data for model testing, and that's essentially observed data that we're trying to match up with simulated outputs. So things like flows, water quality concentrations, we're doing that to evaluate how well the model is calibrated. So in terms of forcing functions, since we're running at an hourly time step, we need hourly precipitation. And in the Basin's library, there's hourly records from many airports, and those records are rigorously QA'd. They're collected and reviewed with rigorous QA. In Minnesota, we've been supplementing them with daily rainfall total data that I get from Pete Goulet over at the state climatologist's office. So he's got a lot of daily totals that we make use of, and obviously we disaggregate that daily data to an hourly time step by finding an hourly neighbor and creating an hourly distribution from the daily total. We do have some applications now that actually have gridded precipitation inputs. There's two models that have the NextRad Level 3 Doppler weather radar, and we also have some models that are making use of NASA's North American Land Data Assimilation System, and that's probably the wave of the future for us, that or some offshoot of that. They're actually working on, for North America, layers of precipitation for North America every 15 minutes on a 15-kilometer square grid, and when they're done, they're planning on going down to a 4-square-kilometer grid. So that'll be nice when that's all done. We need other meteorological data like solar radiation, wind speed, things that we need for the energy balance, which again Dr. Wilson alluded to this morning, things like evaporation and the creation and melting of snowpack and ice pack. You also have to include atmospheric deposition. It's certainly more important in the northern part of the state where the non-point loadings are less. We've got the National Atmospheric Deposition Program for the wet data, so we have really good information on how much nitric acid is in rainfall, so that's really good. We've got the Clean Air Status and Trends Network for dry deposition. There's more uncertainty associated with that. People tend to know how much phosphorus is stuck to a dust particle, but the settling rates are always kind of a tricky thing to pin down, and that's why sometimes we look at other air quality data to help with that. We obviously have to add in the point sources because they make contributions of nutrients to the river, and so they're obviously not part of the non-point simulation, so we have to dump those in. If we didn't include them, then we'd wind up overestimating the non-point flows. And so in Minnesota, we've got about 90 major facilities where we go through the effort of basically entering every day's discharge data from 1995 to around 2009. So you can imagine that the data entry staff at the PCA, when they see me coming, they tend to take off. And I don't really blame them. Although I think most people do that, so maybe it's we also use monthly records, and that's for the miners. There's thousands and many thousands of miners, and so for that we just take the monthly totals and then we divide them up by the number of hours in the month and put that in. Unless it's a pond system and we know the days that it's discharged, then we put that in. So GIS coverages, like a lot of watershed models, we grab a digital elevation model to help with things like slope in the watershed. Now we have LIDAR. We like to use the LIDAR. Obviously, it's got to be hydrologically corrected. We know that sometimes the LIDAR thinks the road is a watershed divide. There's a culvert going underneath it. You need to burn that in and get those watersheds properly delineated. So we do rely on DNR quite a bit for the watershed layers and the supporting hydrography layer. We use a variety of land use layers and soil type layers and put in political boundaries like MS4 because we like to give them their own separate land numbers so that we can quickly extract their loads. And of course we need the exact geographical location of point source discharges. And then we'll always use any other data set that can help our land use category characterization. So for ag areas, if we have tillage transects or coverages of fertilizer application rates, or soil density, we're hungry for that. Up in the Northeast, we've had layers that capture logging practices in old growth forests. The old growth forests, they tend to have an undercarriage that increases infiltration and reduces soil erosion, so that's good to know. Wherever we can get them, we love to have sediment budgets because in our applications, we're not assuming that all the sediment is coming from USLE field wash-off type processes. And the Science Museum, Sean Schottler, Dan Engstrom have been great in providing some sediment fingerprinting data, which helps us constrain how much is coming from field versus non-field sources. And so again, we can't get enough of that stuff. And if we have other models that are already existing, we certainly want those too, and we want to look at both the inputs and the outputs. So the third type is the drainage network representation, and our goal here is to determine relationships between how much water is in the reach and how quickly is the water leaving the reach. And so again, HSPF, the hydraulic model, we rely on hydraulic models to determine those relationships for us. So what we like to get as many survey cross sections and rating curves as we can, and drop them into a model like a HECRAD, the Engineering Center's river analysis system, or some of the DNR staff have used RiverMorph, or PCA staff has used RiverMorph, and develop as many of those relationships as we can. And then DNR has also been great with helping us with lake bathymetries and also the lake outlet structures, and then we've had a lot of locals who have gone out and measured lake outlet structures for us, so that's great. We also need, especially in northeastern Minnesota, we need information on dam manipulation. If the dam is going up and down, that obviously affects how much water is coming over the dam, and our hydrology calculations. And Mike Student, West Root Salonis, he's helped a lot with that because we have these big mine pits that they dewater, and when they dewater, they're pumping a lot of water into the river, and then obviously it'll fill back up, and then some of these hydroelectric plants will take a lot of water out, put it back, but maybe not on the same day. So those are all things that affect flows, obviously. And then lastly, the calibration and validation data needs Again, we're looking at as much flow data as we can get, measured flow data. We look at as much sediment data, both the USGS, the suspended sediment concentration stuff, which tends to do a better job of capturing the sand fraction, but we use anything we can get on. So if we have TSS data, we'll clearly use that. And then, of course, with water quality, we'll use all the grab samples for the nutrients and DOD and chlorophyll A, and it helps to have SON data on parameters that have a diurnal swing. So, like water temperature and dissolved oxygen. And then if we have any information from load estimators like flux, we'll want that too. So we use the weight of evidence approach for each land use, and we try to calculate the water balance, how much sediment, nitrogen, phosphorus, DOD is coming off of per acre of each land use, and make sure they're realistic. And then we do some statistical comparisons on the flows, and obviously we do for water quality constituents, we do point to point. So if we have a water sample on a particular day, we'll compare that to the simulated concentration on that day, and like I said before, we'll do comparison with load estimators like flux. And obviously, you need to have that hourly resolution if you're going to compare DO and water temperature data. So our calibration sequence is first hydrology, then water temperature, then sediment, nutrients, oxygen demand, chlorophyll A, and last but not least, dissolved oxygen. And we do have a guidance document where we lay out the steps for how to build a model and how to calibrate the model and what we think is an acceptable calibration. And this is just a screenshot from that guidance document, and you can see that on the left there's a comparison of simulated versus observed flow statistics, and on the right is our sort of minimum criteria of acceptability. I want to remind people that the last two words in TMDL are daily load. So we are tasked with doing a good job of calculating daily loads in our TMDL effort. And I don't know, some of you might know the Anacostia River TMDL, but there was a lawsuit, and they mostly used annual loads, and the Circuit Court of Appeal said annual loads are not acceptable, that daily actually means daily, and so you have to use daily loads. So I want you to keep that in mind as I'm talking about some of the reasons we want a model that uses an hourly time set. So again, if we're tasked with coming up with sediment daily loads, we're going to have to be able to deal with days where there are storms, because surface runoff tends to drive surface wash-off and transport, and rainfall intensity tends to drive surface overland runoff. And so HSPF uses a Phillips hourly infiltration index approach, which is sort of built on Horton's work, but essentially what it does is every hour it checks for precip and it checks for antecedent moisture conditions, and then it generates surface runoff. And so what that figure is along the bottom, that's actually 24 little hourly rain buckets that we're going to use to illustrate the difference between a low intensity and high intensity rainfall. So I specified the infiltration index to about 0.1 inches per hour, which is a reasonable number, a round number, but a reasonable number. And so if we had a field that was bare and dry and it drizzled 0.05 or 1/20th of an inch of rain for 20 hours, you get a daily rainfall total of 1 inch. But the infiltration capacity would never have been exceeded through that time, and so you wouldn't get any surface runoff, and no sediment transported by water anyway. Now, if we had a same field conditions, but we had a downpour of 1 inch of rain in an hour, you'd still have a daily total of 1 inch of water, but it's all coming in 1 hour. And so if we're able to infiltrate approximately 1/10 of an inch, that's about 9/10 of an inch we can infiltrate. And so that becomes available for surface wash off, and then if there's no surface detention storage, it could eventually get to the reach. So if I was running on a daily time step, I don't have 24 hourly inputs. I've got one daily input, right? It's 1 inch per day. Both of those cases are 1 inch per day. I can't, my file input structure can't distinguish between those two events. So the inputs are identical, the outputs are the same. So I can't capture the rainfall intensity running on a daily time step. And that's, again, since we care about daily loads, it's great to have the temporal resolution of an hourly time step. So if I go back, on the low intensity event, I might have no runoff and no sediment transport by water off the landscape. But in the high intensity event, I might have 9/10 potentially and well over 100 pounds of sediment per acre washing off those bare fields. Now, if I just use the daily time step, many people shoot for the middle, in which case you get maybe a ½ inch runoff for both of those events. Now, if you do that, and I've worked on applications that do that with the Fed, what winds up happening is you have a systematic overestimation of the loads from the low intensity events. This guy, you're getting basically 0 inches of surface runoff, and here you're predicting 0.5. And on the high intensity events, you're systematically underpredicting. And so that obviously has implications for writing up the TMDL. You're overpredicting the high intensity. You're underpredicting the high intensity events. And those are often the events that move the most sediment. So a case study for the pomme de terre, Steve already covered this, and Steve used some HSPF outputs as bathtub inputs, but we also used for the stream reaches. Some of the stream reaches were impaired for turbidity, and there was no gauge nearby. So what we did was we took the simulated flows from HSPF. Eileen Campbell in the Mankato office developed flow duration curves. And what Eileen did is she took the simulated flows from HSPF, she took the actual observed grab samples, and we were able to calculate both the current conditions and then the reduction needed, the pound reduction needed to meet the standard in all 5 of these flow zones. So we had the graph samples already, but what we didn't have is flows, and that's what we used from HSPF was the flows to develop the flow duration curve. And then jumping ahead to dissolved oxygen TMDLs, those of you who are biologists or limnologists might recognize this pattern. This is from, say, a southern Minnesota stream in late July or early August, and this is a plot of 24 hourly DO concentrations. And most of us know that algae respire all the time, but they photosynthesize when the sun is out. And so what you see is often, you'll see, since they tend to photosynthesize more at a greater rate than respiration, when they're photosynthesizing, the concentration goes up, and when they're only respiring, it'll go down. And so we have a DO standard of 5, and so in this case, before dawn, we don't meet that standard. We also have some language about the diurnal fluctuation. We don't want that to be too high. We don't want it to be greater than 5, I believe, or Steve can probably correct me on that. But obviously, if you have hourly DOs, you have at least a chance to evaluate that. Now, if you're running on a daily time step and you're only getting one mean daily DO concentration, you're kind of hamstrung in your ability to evaluate what the diurnal minimum is and what the diurnal fluctuation is. Because if you think about it, you're running on an hourly time step. Some of those hours the model knows we have solar radiation in the model. There are some hours where it's daylight and photosynthesizing is happening, and there are another set of hours where it's night and it's respiration only. Whereas if you're running on a daily time step, you can't divide day and night. So again, if we're going to complete dissolved oxygen TMDLs, we want a model that has the processes of algal respiration, algal photosynthesis. Again, photosynthesis doesn't happen at night, so it's nice to have that temporal resolution to know when it's night. And also, you want to include nutrient concentrations and sediment concentrations, because all of those have the ability to impact the growth and death and photosynthesis and release of nutrients by algae. So we did it, again, Eileen Campbell did a DO TMDL on the Little Cobb, which is a tributary to the Sueur, and we looked at the flows at and above 7Q10, because that's where we have to meet the standard of staying above 5 milligrams per liter. So we calibrated the model to baseline conditions. There was a point source, but it was 0.5% of the total phosphorus load. And again, I had to run scenarios because in the conventional parameters, you don't need to run scenarios, but I ran some scenarios where I reduced the phosphorus so that algal growth was phosphorus limited and there was less respiration and photosynthesis. So we start out with a situation similar to this, and that was about the minimum, was about 2.5. And when I reduced phosphorus concentrations, I got to the point where this was the case where you can see that the minimums are lower and the high concentrations are lower as well. So we met, that's what we did for Eileen. She wrote it up and we met the TMDL. A couple more case studies, I'm almost done here. A couple more case studies that are for pollutant trading. Because we had that low DO TMDL at Jordan, there was a basin permit written in 2005, and the PCA wanted to enable trading, so there was some pollutant trading between non-point and point as well as point and point. And so there were 3 cities, smaller cities, including Olivia, in the western part of the basin, that they were having their permits lowered. They were going to have to spend money to treat more, but Mankato had additional capacity, and so we allowed them to trade. But since our endpoint was Jordan, and phosphorus is assimilated along the way, we had to have a trading ratio set up. We used the model for that. So if you think about it, if you dump 100 pounds of phosphorus at Jordan, you have 100 pounds of phosphorus at Jordan. But if you dump it in at Mankato, maybe only 88 of those pounds make it to Jordan, and 12 get eaten up along the way. And so then the further away you are and the more you're off the main stem, the less it makes there. So if you're trying to get a reduction, if you're trying to reduce 100 pounds at Jordan, you can do that by reducing 100 pounds at Jordan. But you might have to reduce by 110 at Mankato because only 90% of it or 91% of it makes it there. So we use HSPF to calculate the trading ratios. And then 2 years later, the Mankato wastewater treatment plant permit came up again, and engineer Mark Tomasek in the permitting division, he asked me if I could run some scenarios with HSPF where we lower the flow and the phosphorus loads and the BOD loads coming from Mankato to see what would happen at that compliance area at Jordan. And so we lowered the concentrations year round, and then we tried just doing it in the spring and summer, and then just in August and September, and that's how we wound up with 150 different model combinations. But Mark looked at that output and he used that to figure out what we needed to meet the standards, but not be overly onerous on our permitted partner, the Mankato wastewater treatment plant. And then last case example, I provided to some of our Stressor ID folks. I provided mean daily, mean monthly, and mean annual flows, sediment concentrations, nutrient concentrations. I provided hourly dissolved oxygen output, and I've also been able to, there's a way to extract all events above a certain concentration. So Kim Ryan wanted to know, give me all the events when the TSS concentration is above 65 or the chlorophyll A was above 40. And she used that to make some plots. Here she put the nitrate data And she basically plotted all the times when a certain reach in the Sueur was above 3 milligrams per liter and above 5 milligrams per liter, because those concentrations have the potential to be stressors. So here's where we are in terms of progress. The dark blue sub-watersheds, we have at least one version of the model completed. In the Minnesota River Basin, we've actually had multiple versions of the model. We try to keep them up to date. The light blue Puck 8 watershed, those models will be done. Those models will be done by June 30th of this year, and the white watersheds are not currently underway. And so people always ask me, when are we going to be done? Or when's this model going to be done? Well, the sad truth is the model will never really be done, because we will keep collecting monitoring data. We'll keep finding impairments. And so then we're going to have to keep extending our models into the future. So right now our models go, most of them go through 09 or through 2012, but we'll periodically want to extend those time series. So we'll have to append the meteorological records and the point source records. If we have a new impairment in a place where we need output, we might have to split the Hub 14 into smaller pieces. And we'll have to revisit the water quality calibration, especially if, say, the original model, there was no water quality data at a particular site, but now we're adding 3 more years, and they just started to collect water quality data, so we have to be prepared to do additional calibration. Summary of limitations, it obviously has extensive data requirements. Calibration is required. It's got limited spatial definition. It's not a grid-based model. We're limited to freshwater systems. Flow is unidirectional. It's not a hydrodynamic model that calculates the elevation of the water surface and can have water flow in different directions. It's not able to do that. It's got a strong representation of impervious surfaces, but it does not include the explicit representation of pipes and culverts like SWIM does. It's a complex model, and if you're getting into it, they recommend you take some training, because the development of expertise takes time. And because of that, Galen Reese, again, the guy who I couldn't break, that his 100-year plan was really a 300-year plan, he wanted people who weren't experienced with HSPF to be able to get data out and to extract, to get data out and to basically run simple scenarios. And so, because of that, we funded the further development of a tool that RESPEC had begun to develop on their own, the Scenario Analysis Manager. And Jason Love and Seth Kenner are about to come up and talk about that, but I'm just going to end on the fact that HSPF probably gets us to the purple box, and hopefully things like SAM will get us over to the green box. And I think, well, do I have another 3 minutes? I really don't have anything else to say, but I can talk about, other stuff. But if you want to read about the QA or something, but I don't really want to talk about it because I think I've tortured you enough.